Okay, so in today's lecture, we're actually going to solve this and propose the algorithm to minimize the MLE estimate and propose the algorithm to find MLE in the Gaussian mixture models. MLE. So I want to remind you what is the log likelihood in this cases. This will be log of likelihood this will be and basically I think we already and write it up. So this is summation of 1 from 1 to the n logarithm of pi of x of I conditional on theta. Right, so and I'm going to marginalize all possible of cluster membership, so which is our hidden variable. So here then this becomes summation right here from zi from 1 let's and then let's call it c here. I think that would be easy. C from 1 to the k, probability x of I, then zi equal to c, conditional of theta. So right here is the cluster membership. And so which is a hidden variables. So and so and then that's how I'm actually and written out this and the likelihood. But the issue is, as I mentioned, this whole thing is very hard to optimize. It's just because of one of the parameter in the theta has been to be the sigma here. Sigma is something like it's positive definite, which in general, I mean, it's a very hard constraints, and you need to, so need to impose when we're trying to optimization and when we're trying to optimize it. So so it turns out this is very hard to optimize. So then we're going to using a slightly different idea. It's called expectation and the maximization algorithm. So this is called EM. So the whole idea is, I mean, it's basically like an alternative and optimization idea. It's we actually and want to separate this whole and optimization problem into two steps. The first step is called E step. So E step is called expectation step. And the second step is called M step. So M step is maximization step. So basically, we're going to take these two steps alternatively. So in this like E step, this is basically we want to estimate the hidden variables. Which is our, I mean, this case is that would be Z. for the maximization step, it's and we use the full observation to calculate and to calculate MLE of those parameters theta here. So this has two steps. The first step is just to estimate a hidden variable z, and then using this information to estimate the parameter of theta. So we do this alternatively. So this is very similar to the k-means and the k-means optimizations. And of course, we need to iterate this process until everything start to converge. And of course, this whole thing and expectations actually depends on the parameter, and this parameter right here, actually depends on those expectations. So this is one versus and connect to another's. So this is, and then that's why we have to and consider everything like alternatively. So this is this is the whole idea. But the math, underneath of this is quite quite intense. So that's why I would like to elaborate. In more detailed ways. So here is the trick. The trick here is okay. So why everything is so difficult here is because if we actually look this part, we have the logarithm of the summations, right? So this part is very hard to work with. Somehow, if we can switch the order of summations and the logarithm, this will be significantly easier. But of course, and we cannot switch the logarithm and the summation easily. That's not a correct transformation. But maybe we can utilize this whole idea in a different ways, right? So, and this is hard. This is easy to calculate and easy to optimize. Okay, so this is some logic underneath of this. So the first thing is we're going to consider a set of some distributions over some hidden variables. So this is something I'm going to step back and to think slightly different ways. So we consider some distributions. I'm going to call it Q of Z of I over Zi, which is the hidden variables. So the logarithm of the log likelihood can be written as the following. So I'm going to multiply this QZI and it divided by QZI. So it's nothing changed, but so this is equal to I from 1 to the n, the logarithm of summation C from 1 to the k. But here I'm going to say Q of Zi equal to C P x of I Zi equal to C conditional on theta divided by Q Zi equal to C. So this is basically and multiply a quantity and divided by quantity. So this is nothing being changed here. So we are going to using Jensen's inequalities. So what is Jensen's inequalities? That is if phi, if summation of I of AI x of I, so this is bigger equal than summation of I of AI of phi of x of I. So basically so I can switch, and I can switch the order of summation of phi, but this is, it's not equal sign, but just bigger than equal. If phi is for any concave functions and concave phi's, and also summation of AI has to be equal than 1. All right, so unfortunately, log is a concave functions. So we think about this log function right here. It looks like this, right? So what does the concave function look like? It will be look like this. So everything looks like cave, like one single like top concave function. So this is called concave. And to be more like precise, the definition of concave is if I have a 2-point, if I connect these like function value right here to pick the middle point of the function values, this should be small or equal than the function values evaluated at the middle point. So this is called concave. All right, but unfortunately, logarithm is actually a concave function. All right, so if we using this fact, then we can switch the order of the logarithm and the summations. So this is bigger equal than summation I from 1 to the n, summation c from 1 to the k, logarithm of sorry, this is, and you can think about this as being a, right? So this is basically my a, AC, and your phi, and your log is your phi. So then this becomes your q of zi equal to c, then logarithm p of x of I, c of xi equal to c, conditional theta, q zi equal to c. Okay, so here this is bigger than equal. So you can see right here, and we have some arbitrary distribution of q. Here we have arbitrary distribution on the denominator. I'm going to define this whole thing as summation of I from 1 to the n of this, I'm called E of theta of z of I conditional on x of I. Okay, if we sum them together, so this is, I'm going to call the whole E of theta, but it is zi I from 1 to the n conditional on x of I from 1 to the n. So this whole thing right here, it's actually has a name. It's called evidence lower bound. It's called ELBO. So this is, I mean, the reason it's called lower bound, it's actually, I mean, the reason is because this is actually the lower bound of the log marginal likelihood of the and of my mean function that we're interested in. So this is lower bound of log likelihood. Okay. So and we see this lower bound is bunch of the summation here, right? From I1 to the n. It's a summation of n terms. So we can and actually like expand it out to see for each of details right here. So let's just consider this portion in great details. So this each sum right here summation of c from 1 to k q ci equal to c log p of xi, that's the joint distribution. And the marginal distribution. Sorry, I mean this arbitrary distribution of q right here. So let's, I mean, look at these things carefully. So here, like on the top right here, this is a joint distribution. We can use conditional probability to write it out. So this is probability zi equal to c, conditional on x of I and theta. Probability xi, conditional on theta. Over zi equal to c. So then this is equal to summation c from 1 to the k. We can split up this multiplication right here because this is 1 and multiply to another. This is q of zi equal to c. The logarithm of p zi equal to c and conditional on x of I and theta and divided by qzi equal to c. Then plus, so and the second term, summation, same summation, logarithm q ci equal to c. Oh, wait, I think I was wrong here. So this is just like that because we basically, and what we do is we consider this everything in the logarithm into two parts. One part is this, another part is this. Right, so then this summation right here only sum with the q zi equal to c, which this right here becomes a constant. But of course, this we can I mean, if we just simply sum this up, this is just give you 1, right? Because that's a definition of the distribution and an arbitrary distribution of Q right here. So that means that we can just get rid of this because this is equal to 1. I mean, at the end, we are getting something like the first term looks like this. The second term looks like that. So what is the first term? The first term has a name. Actually, it's called KL divergence. KL of Ci given P of Zi of x of y and theta. Plus the logarithm x of y and theta. So what is the KL divergence mean? The KL divergence is summation of QZ logarithm of QZ over PZ. So I mean, this is called KL divergence. Yes, because I mean, this is QQ here, right here, and the QQ is on the denominator, so that's why we have a minus sign here. It's called KL divergence. Between two probability distributions, P and Q's. So this has a, and the KL divergence has a very important property. The very important property states the follows. The first thing is this KL divergence is always bigger or equal than 0. And this KL divergence equal to 0 if and only if P equal to Q. Okay, so this is a very important part. The second thing is we can actually maximize the lower bound. We can maximize this evidence lower bound altogether. Okay, so let me just erase this part. Because I mean, if you look at the first component, so we know KL divergence is always bigger or equal than 0. Then this first component is always smaller or equal than 0. So, and in particularly, it is maximized this term is maximized when we set QZI is equal to PZI conditional on xi and theta. So this is basically, we can, Q is arbitrary distributions. We can just set Q is equal to this. Then this evidence lower bound is maximized. So then the evidence ELBO is maximized. And the most important part is, if we set these things to be like that, then this KL divergence part is just equal to 0. Then this ELBO only have the second component, second part, which basically this part is 0. We only have a second part, which is logarithm of probability of x of I, and conditional on theta. And of course, we have to sum them together for I from 1 to the n. This is nothing but log of likelihood function. So that and this is, so basically, if we try to maximize the evidence lower bound, this is the evidence lower bound. The maximum of evidence lower bound is reached when we set this Q star was equal to function P, and right here. So this is nothing but something called posterior distributions. So it's a probability of Zi conditional we observe of Xi and theta. And also, and this is a tight and a tight lower bound. So ELBO is tight lower bound. So what is the tight lower bound means is, although evidence lower bound is less equal than the log likelihood, but it can reach to the point of log likelihood at certain thetas, if possible. So, and if we try to maximize the ELBO, it will be the corresponding log likelihood. So that means tight lower bound, i.e., so ELBO, so log likelihood is bigger equal than like ELBO, so which is a theta. But sorry, I think it's ELBO. It's not only theta. It's a function of Q here. But if we trying to maximize the Q of ELBO, so this is actually recovered the log likelihood. All right, so this is basically tells you ELBO is a tight lower bound. Okay, we can using all these knowledge that we learned to construct these algorithms. So construct EM algorithm. So the key here is we need to update the thetas such that the log likelihood value is increasing. So that means the key point is at each t iterations with theta t, right? So this theta t is not theta t's power. On the other hand, it's just the theta value at t iterations. I'm going to construct something called an auxiliary. So auxiliary function. So some like function to help me, which I'm going to call it Q. Q is a function of theta, but also take input with the current theta t here. So this is a very important function. So theta t here is actually a specific parameter value. Theta is the variable. So this is the variable. So this is some parameters. Okay, so this is a fundamental different part. All right, so this is equal to double sum I from 1 to the n, C from 1 to the k. Here I'm going to, and let me write it here because I don't think we have enough space here. So this is right here. I have summation I from 1 to the n, C from 1 to the k, probability of Ci equal to C, conditional on x of I, and the theta t. Okay, so here we're using theta t, so that means that is a fixed value here. Logarithm of p of x of I, z of I equal to C, conditional on theta over probability of Zi equal to C, conditional on x of I, and the theta t. So if we look things closely, the only variable shows up theta right here, which is the parameters of the, the variables of the functions. The parameter theta t actually shows up on these two occasions, right? So this is actually a different part. And you can see this is right here, it becomes our posterior distributions. If we set this as a, so my posterior distribution, so this perfectly means this is equal to, I already assigned my QZI equal to this posterior distributions. So the key things is we know this and so this whole thing is basically the evidence lower bound. So I mean, this just like strictly follow the definition of the evidence lower bound. I mean, if you replace this whole thing by the QZI equal to C, this is nothing but the evidence lower bound. So so this is ELBO of log likelihood. So that means log likelihood should be bigger or equal than Q of theta and theta t for any theta, right? So for any theta, this should be true. And the equality is hold if and only if theta t is equal to theta. So the only time that these two are the same is when theta equal to theta t. So then, and basically the the K and the KL divergence just becomes 0 in this part. So with these properties, we can propose the algorithm accordingly. So for t equal to 1, 0, 1, 2 to update theta. So then the theta t plus 1 is equal to argmax of theta of this Q function of theta and the theta t. Okay, so this is basically the EM and the center part of the and the maximization part. Okay. Why somehow maximize this Q function is equivalent as maximize the log likelihood? Because we can prove as follows. This EM is ascent for maximization of log likelihood. So what does that actually mean? It is Q theta t plus 1 and the theta t. Since this is, we maximize with respect to theta, so this is bigger equal than theta t and the theta t, right? So this is due to the EM algorithm. But we know if theta is equal to theta t, EM equal to my parameter, this is nothing but my log likelihood evaluate at theta t. And by definition, this is and this Q theta t plus 1 theta t is the ELBO of log likelihood evaluate at theta t plus 1. So this is because ELBO at theta equal to theta t plus 1. This is because of my EM maximization. This is because the equality is reached when theta is equal to theta t. Right, so as the result, somehow if we trying to maximize this Q functions, it is equivalent that we are trying to maximize this log likelihood functions. And of course, a note, this log likelihood function is non-convex. So it can only reach some local minimums. All right. So a good illustration is given as follows. I think this is a good illustration. So for example, right here, let me using Let's say this is just a 1D theta right here. We have some like log likelihood function. This Q function looks like this. So this Q function may look like this. This is Q theta t at theta equal to theta t. Then these two functions and the function value are the same. And also my Q is always smaller equal than log likelihood. And my Q theta t and the theta t is equal to log theta t. And also, if we try to maximize the theta of the function Q theta, right here, this will be my next step of theta t plus 1. It can be shown this value, log of L theta t plus 1, will be bigger equal than log of L theta t. So this is a good idea why, and what is the, this like ELBO function look like, and why and why this whole thing is and it's always ascend. And of course, this is not the optimal like theta here. So the optimal theta here is right here. But you can see as we continue to iterate the theta t, and we can guarantee, this is on the trend that go into this like and the local maximum here. Sorry, this shouldn't be meant as minimum. We are not taking the negative, we are just taking the log likelihood. That means there will be local maximum instead. Of course, the global maximum is not, guarantee in general, we can only reach the local minimums. Sorry, the local maximums. Okay, so this gives you some good idea and what I'm actually working here. So this is a very generic cases. So and here we didn't actually apply anything on the Gaussian mixture models yet. We just and this whole argument works for arbitrary models. So this is a very important part. If anything that your log likelihood looks like this, there's a potential that you can work with. As far as you are working with some latent variables or hidden variables, you can always use this argument to build this EM algorithms. Right? So this is this is basically very much universal methods, because right now from like here we didn't actually imposing any model yet. Okay, so let's just be more specific, because we are working with Gaussian matrix, right? So EM for Gaussian matrix. So as I said, so it has a two-step. So first step is the expectation step. So the expectation step is basically we need to calculate and we need to calculate those and the latent variables based on the current parameter settings. And basically in this case is we need to evaluate the posterior distributions. So the whole idea is to calculate the posterior distributions So P of Zi conditional on x of I and the theta t for conditional on the theta equal to t and the theta t, which in this case is my theta t is equal to, I have pi c, mu c, and sigma c, t, 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 c from 1 to the k. So this is the expectation step. And how to calculate this posterior distribution right here. So this posterior distribution is given as follows. It's given as probability of x of I, Ci equal to C, and theta t, and multiply the Zi equal to C, conditional on theta t, over probability x of I theta t. So this is, I mean, nothing but base rules. But we know all these conditional probabilities. The first one is nothing but Gaussians, because conditional on, we know, cluster member is the C. That will be just a Gaussian distribution. So this is nothing but a Gaussian distributions. So evaluate of x of I, conditional on mu ct and the sigma ct. And multiply the probability of the cluster membership equal to C. So this is nothing but pi ct. Okay. Then the bottom is we need to sum all possible situation that for all possible clusters. So this is equal to, I think this Ci equal to C. All right, so this is summation. I'm going to call it J here, J from 1 to k, Gaussian distribution of mu jt, sigma jt, and pi jt. So basically, this is my posterior distributions. For any I 1 to the n, and C from 1 to the k. All right, so I'm going to call this as a name. Okay, so this is and going to be defined as phi C of I at t iterations. So there's a lot of like notations here. All right, so this is how we define this posterior and a posterior distribution. And of course, this is just a PDF of my Gaussians at and with the mean of the mu ct and the covariance is sigma ct. All right, so these posterior distributions actually give you the and actually can make predictions here. So we can put all these probability and posterior and the distributions into a vectors. So here we're going to define the phi. I'm going to define a phi is I and t, which is phi 1, it. So basically, we stack all these probability together. right? So this is an actual probability vector. So that means each component will give, and it need to be summed to be 1. So what I'm going to do is I'm going to say my membership, Z of I, which is unobserved hidden variable, is equal to argue max of theta C of I T of C. Right, so basically, this is my posterior probability right here. Then my membership is belongs to the argument, which makes my gives the highest posterior probability component. Right, so this is kind of very similar to this prediction step of this logistic and the logistic regressions after we apply the softmax. So I want to remind you, after we apply the softmax, that becomes a probability vectors, and all we need to do is find out the component and such that to maximize and the component of the and the probability. But this here and here is my highest, I mean my like posterior probability vectors. So we want to find out the component such that the posterior probability component is the highest. So this is my prediction here. So this is basically my prediction part. Prediction step of the cluster. So of the cluster membership. So this is expectation step. So next will be maximization step. So maximization step is the key is we are going to update the parameters given this and the clusters informations. Given the cluster informations. Right, because we already know from the expectation step and gives the cluster terrain for all the point. But so maximization, the whole idea of the maximization is we want to maximize this Q function. Right, so, and I want to remind you, this Q function looks like this. Summation I from 1 to the n, C from 1 to the k, phi c, it, and the log of like this, and the phi c it. And here we already compute this posterior distributions right here and posterior distribution right here. We can just and directly used from E step. So equivalently, because we need to and trying to find out all possible. To find out the best parameter for pi c, mu c, and sigma c, and we can actually and maximize them. So each individually. So this is equivalent as we can find out pi ct plus 1 and the mu ct plus 1, sigma ct plus 1 equal to argue max pi c mu c sigma c summation. So basically, we're going to switch the order of this like summation part. I from 1 to the n, phi c I t, and the logarithm of x of I ci equal to c, conditional on pi c, mu c, and sigma c. And right here, this is the joint distribution. So for this joint distribution, we can calculate these terms explicitly. And then this is, for c equal to 1 to the k, right? So this is, so once we switch order of the summations, this maximization terms and it can be performed for each individual c's and for each individual clusters. So right here we have so this becomes argmax pi c mu c sigma c. So this is summation, and we already have this posterior distributions. This posterior distribution is coming from the E step. So the logarithm of pi c of probability, so which in this case is the Gaussian of x of I, conditional on, and we have nothing to do with the pi here, so just mu c and sigma c. Then we can split it up. So that will be just, and we can split the term for the pi c and the mu c and sigma c. So we can have a pi c on this term. This is summation I from 1 to the n, c log of pi c, right? And a summation argmax mu c and the sigma c from 1 to the n by c it mu c and sigma c. So this is just like nothing but rewrite and this equation separately. So we are and maximizing pi c separate from the mu c and the sigma c. And also this pi c has a constraint subject to pi c has to be, sum of pi c has to be equal to 1 because this has to be a probability. And sigma c is positive definite. Okay. The beauty of these things is this has analytical solutions. And that's one of the homework. In homework, you are going to actually solve this analytically. So basically, if you want to solve this analytically, I mean, this pi ct plus 1 is nothing but the following: 1 over n of summation 1 to the n of my posterior distributions. And my mean here is the weighted mean and the weighted average of the weight of which is my posterior probability. Yes, VI. And also the sigma ct plus 1 summation I from 1 to the n. This is also weighted and weighted covariance ensemble covariances. So this is weighted ensemble covariances. And the weight value is my posterior distributions. Transpose. And it divided by summation I from 1 to the n phi c it. Okay, so it's very similar to what we already did for the single multivariate Gaussian distributions. But the difference is in everything here, it's not just a simple weighted and a simple like sample mean and sample covariances. So we are getting the weighted mean and the weighted covariances here. And the weight is nothing but and being given by the posterior distributions. So this is a homework problem. So the beauty of this is this constraint right here is satisfied automatically, right, for pi ct plus 1. And also this sigma, which is my covariance, if we construct our covariance in this way with weighted sample covariances, this is positive definite, it satisfies, I mean, satisfied automatically. Satisfied automatically. I mean, it's because we have some like VV transpose and a structure right here. V is the column, V transpose a row. VV transpose becomes and automatically a positive definite matrices. So we don't need to worry about whether this constraint is satisfied or not. The beauty of EM algorithms is all these constraints is being satisfied automatically. All right, so let's just, I mean, we have like and studied this for quite long, but let's just summarize everything here. Right, so step 1 and step 0, initialize the pi c pi c 0 and mu c 0 and sigma c 0. Well, I mean, you can like initialize smartly. You can like initialize randomly. Again, this initialization is also quite tricky. Step one is the E step. You are going to calculate the posterior distributions. Phi C I T. This is equal to basically pi CT and the normal distributions of X of I conditional on mu CT and sigma CT. Summation at J from 1 to dk pi JT X of I mu JT and sigma JT. Okay, so you calculate this posterior distributions, which is, and you can put everything into a gigantic matrix. You can call this matrix a phi, which is you have phi 1 t until we have phi n t. Right, so this is actually a m by k matrices. So each row, I mean, so will be a probability vectors. So each row, I mean, you actually sum up to be 1 here. But each column, I mean, so it's not necessarily sum up to be 1. Then step 2. So we update the pi CT plus 1 and the mu C T plus 1 and a sigma C T plus 1 from by what? By this right here. All right, so these are the formula right here. You are going to update that according to this weight. So if you look things right here, this is we fix the C here. And sum all possible from I from 1 to the n. This is equivalent that we fix one column of C, then sum for all the component on the C. So that's why this value is not equal to 1. Right? So and the summation of each column is not equal to 1. So update this according to this formula. Step 3, go back to step 1, unless stopping criteria is reached. For example, all these parameters, it doesn't change too much, right? I mean, it's already being fixed, then you're gonna stop. So that means this is actually the E step. This is actually the M step. So that's it, and so that's why this is called EM algorithm. You just keep updating and iterating here. All right, so last part of theory is it's also very interesting. So in the previous and week's lecture, we talk about EM algorithm. And obviously EM algorithm is a very important part. So in the past in the past lectures and right here, and keep talking about EM algorithms. But in the last week, we talk about k-means and the Lloyd and algorithms. But this is a special case of EM. So the reason is k-means is actually a special case of Gaussian matrix. So you can think about k-means is, and I mean, if we want to using k-means, the data has to be generated as follows. We assume step one, all of my sigma c is round shape. So that means my covariance is a constant times identity. And my pi c is just uniform 1 over k for all the clusters. So that's why we can just use the mean directly rather than just weighted mean. So in the EM algorithm. So then, that's not step one, just the first part. In second part is what we do in the E step is we approximate E step by and hypothetically the E step is phi c of I. Then this is the that we just take the argumax of C. This will be your membership of Z of I. And what in k-means says this phi c of I is only an indication function that Z of I equal to C. So that means the probability to be in the other and clusters to be 0. It just basically replace this posterior probabilities with hard cluster assignment. So this is a hard cluster assignment. So that means during this E step here, once this point is being assigned to the cluster C, that the probability to be in the cluster C will be 1, and the probability to be in other clusters will be 0. But in EM algorithm, because we have this posterior distribution right here, so that means the closest one that will have the highest probability component. Although if we want to make predictions, that will be the cluster that we will predict. But on the other hand, there will be other clusters have non-zero probabilities contribute to it as well. So we cannot just simply ignore that part as well. But in k-means, we just replace this posterior probabilities with a simple hard assignment, hard cluster assignment. So with that, And this analytical solution in this M step will reduce to our k-means iterations. So then, and k-means, and so that's why k-means, well, like favors to like round cluster with equal size. Okay. So this is, and this part is commonly asked questions during data science interviews that you should know that very well. What is the connections between k-means and the Gaussian matrix? So this is a two major part, and which is basically k-means is essentially special cases in the Gaussian matrix with these two special assumptions that we impose. And of course, if we make this such kind of simple assumptions, we can have this analytical solutions of the M steps, and everything just reduced to k-means, like alternative and optimization schemes right here. But as the result, k-means only favors with a round cluster with equal sizes. So that's why in many cases it won't work very well. And particularly when the data is highly skewed or with the various different densities. Okay, so that's everything for the theory of Gaussian mixtures. In the next part, we're going to implement this from scratch.